Fructose, this is a ketohexose, whereas glucose and galactose were aldohexoses. Look at the aldehyde group in glucose, look at the aldehyde group in galactose. In fructose, we have a ketone group right there. And so this is a ketohexose. It occurs in fruit juices and honey and is a constituent of the disaccharide sucrose. It is a major constituent of the polysaccharide inulin, a starch-like substance present in many plants such as dahlia tubers, chicory roots, and Jerusalem artichokes. It is the sweetest of all the common sugars, being actually twice as sweet as glucose gram per gram. This accounts for the super high sweetness of high fructose corn syrup and honey. And so sweet corn has been bred to produce a lot of sucrose or fructose because it's extremely sweet. And that's the advantage of high fructose corn syrup, is that it's super sweet, so it's a very effective sweetener. Fischer projections of monosaccharides. The keto or aldehyde group is placed at the top of the molecule. Each interior carbon atom is generally shown as an intersection point between two lines. And so when you have two lines crisscrossing, that's a carbon there, because four things come off of a carbon. And the hydrogen atom and the hydroxyl group attached to the interior carbons are written to the left or right of the projection. So here's D-glyceraldehyde. Why is it D? Because your very bottom chiral carbon, the OH is on the right, just like D-glucose. Again, that tells you nothing about how it rotates light. That would need a positive or a negative to give you any indication of the optical activity of that molecule. But this is D-glyceraldehyde. Here we have L-glyceraldehyde. Again, your very bottom chiral carbon, and honestly in this case your only chiral carbon. The OH is on the left, like L-glucose. Epimers. These are monosaccharides that differ only in the configuration at a single chiral carbon atom. In the case of glyceraldehyde, the chiral carbon is atom 2. And so, here's an aldotriose, glyceraldehyde. Aldo, and we're looking at the structure of glucose and other aldoses. Aldotetrose means 4 carbons. We have D-erythrose and D-threose here. And then 5 carbon, the aldopentoses. We have ribose, arabinose, xylose, and lysose. Lysose. In aldohexoses, allose, altrose, D-glucose, D-mannose, D-gulose, D-idose, D-galactose, and D-talose. And here we see their Fischer projections. Draw the enantiomers of D-allose and D-talose using the previous slide. Well, here we see D-allose and L-allose. Here, because you were given D-allose right here. And it's kind of easy because all the OHs are on one side. And then L-allose. We have 2 mirror images here. D-talose and L-talose. And again, we get D-talose from our slide here. It was given to us right here. And then you draw the mirror image to get the L-talose. And again, this is not something you'll have to memorize at this stage of chemistry, so these materials would always be with you when you're going to take an exam or use it. Kiliani-Fischer synthesis is a laboratory conversion of one aldose into another aldose containing one more carbon atom. And so here we use hydrogen cyanide to form a cyanohydrin and hydrolyze the nitrile group to a carboxylic acid group. Again, And then we can reduce that carboxylic acid group with a sodium amalgam to form the corresponding aldehyde. Hydrogen cyanide, while super toxic, is a lot of times for an organic chemist the absolute easiest, most convenient way to add one single carbon to a molecule, which is why it's used. And so it is very dangerous and it's toxic, but it's super useful because it's a natural source of negatively charged carbon, which is nucleophilic, which will attack really easily. And so basically just our cyanide, whoops, let's draw that better. Our cyanide with the negative charges on the carbon, this just attacks this carbon, whoops. It just attacks that carbon, because that carbon is partially positively charged, because this oxygen, if we remember from chemistry 1, oxygen is a lot more electronegative than carbon, so it's pulling up on the electron density, making this carbon a little positive. So it attacks there, kicking those electrons up, and then that negative charge grabs an H+, which is why you see it's protonated here. And then H came from there. And so now we have this cyano group, the nitrile group here. We hydrolyze that like we saw in that last chapter with nitriles. And you get a carboxylic acid group, and then using a sodium mercury amalgam we can reduce it to an aldehyde. Now when you're doing normal chemistry, you get both enantiomers of the carbon that gets attacked, because you could form this compound or you could form this compound. 50% of the cyanides will attack from above this carbon and 50% will attack from below, giving you a 50-50 mixture of both compounds. And again, that's why with just standard organic chemistry it's really hard to make enantiomeric pure compounds, because you always get a 50-50% racemic mixture at any chiral carbon that you produce, without specific chiral catalysts to favor one over the other. So we'll show the conversion of D3-ose to 2-D-pentoses using the Kiliani-Fischer synthesis. Again, you first attack with cyanide, and remember, half the molecules will attack from the top, half of them will attack from the bottom. Half of your molecules will have this conformation at this chiral carbon, the other half will have the opposite conformation at that chiral carbon, depending on where the cyanide attacked from. And then we hydrolyze the cyanide into a carboxylic acid, and then we reduce with our sodium mercury amalgam into an aldehyde. Pyranose sugars have a cyclic structure. And we have 6-membered rings here, because one of the OH groups, the electrons in the oxygen attacked, it'll attack either the aldehyde or the ketone group and form a hemiacetal here. And so straight open chain D-glucose is so reactive that almost all the molecules quickly rearrange their bonds to form 2 new cyclic structures. And again, 50% of the time it attacks in one direction, 50% of the time it attacks in the other direction, and so we have these two compounds. This brings us to the anomeric carbon. This carbon is an anomeric carbon. Notice it's attached to 2 oxygens. And the OH can be up or down. If it's down, this is an alpha bond. That's where this alpha is coming from. It means this OH is in the down position. Beta, right there, means this OH is in the up position. So when it's a straight chain compound, it's D-glucose. But when it cyclizes, you form either alpha or beta D-glucopyranose. And again, anomers, 2 cyclic diastereomers that differ only in their stereoselection at the anomeric carbon. Mutarotation is a phenomenon that occurs when the alpha or beta forms of glucose are put into solutions and allowed to stand for several hours, because they interconvert into each other. Alpha becomes beta. They're always interconverting. And notice here it undid itself. And again, these electrons on this oxygen can now it's in its straight in the middle there. It's in its straight chain, open chain form. But these electrons can either attack from the top of this carbon or the other way, from the bottom. And that's what gives you your two opposite conformations there at the anomeric carbon. Modified Fischer projection. The alpha form has the OH on the right of the anomeric carbon. The beta form has the OH on the left of the anomeric carbon. So this is alpha. And again, this oxygen here attacked that carbon to produce this hemiacetal. In alpha, it's on the left. Beta, it's on the right. And so it's this carbon, this oxygen right here, is what's doing the attacking. Haworth perspective formula represents the molecule as a flat hexagon. The H and OH groups are above and below the plane of the hexagon. So you're trying to imagine this three-dimensionally, where the up ones actually indicate above the plane of the hexagon and the bottom ones are below it. Galactose, same structure as glucose, except the configuration at carbon 4 is reversed. Notice in glucose, we have this conformation, and galactose we have this conformation, making them epimers. They're exactly the same, except the conformation at one chiral carbon is different. They're both D because the very last chiral carbon, the OH, is on the right. Galactose. It's an aldohexose like glucose, and again it exists in the alpha and beta cyclic pyranose forms when it self-cyclizes, because that alcohol moiety, the OH, attacks the anomeric carbon to form these two isomers. Structures of galactose and fructose. Fructose is a ketohexose. It exists in the open chain in cyclic form, and again same thing happens. This OH here will attack this carbon. But because the ketone is not at the end now, it's at carbon 2, now we only have a 5-membered ring. And this CH2OH group is over here. So carbon 6 is not part of the ring. So while glucose and fructose are both 6-membered monosaccharides, as is galactose, so you have glucose, galactose, fructose. They're all 6-carbon monosaccharides, but glucose and galactose make a 6-membered ring, whereas fructose makes a 5-membered ring, because the attackable carbon, the ketone, is at carbon 2 instead of a carbon 1 aldehyde, like in the aldoses of glucose and galactose. So write the abbreviated Haworth perspective formulas and names for the two anomers of D-galactose. Well, you're going to get alpha and beta. You get beta D-galactopyranose, and again beta, the OH at the anomeric carbon is up, just like in beta glucose. And we get alpha D-galactopyranose, because the OH at the anomeric carbon is down. It's alpha. Hemiacetal, again, the structure consists of an ether linkage and an alcohol structure on the same carbon atom. So that is why we're calling that a hemiacetal. Because on what used to be either an aldehyde or a ketone carbon, now I have one OR group that's ether-like bound, and on the other side there's an OH group, like an alcohol, making it a hemiacetal. A true acetyl would have two ether-like bonds on both sides of the anomeric carbon. And again, hemiacetals, cyclic structures of monosaccharides. And we'll notice our anomeric carbon is always a hemiacetal here, because it has the ether-like linkage on one side right here, but it has an OH group right there. Again, fructose. Ether-like linkage on one side of the anomeric carbon, but an OH on the other side. And 5- and 6-membered hemiacetal rings are very stable, which is why 5- and 6-membered rings form a lot. If you go and take further organic chemistry, you'll see that there is just more stability with 5- and 6-membered rings, and so they're easier to form and they form more spontaneously.